Log on, tune in, find out. Another good idea from Cambridge.
Welcome everybody to our seminar, part of our special period in inverse problems. Today is a big honor to introduce Professor Nakamura from the University of Hokkaido. He's known to be a leading expert in the field of inverse problems, and I've been particularly attracted by his work in elasticity for the direct and also for the inverse problem. And also recently he has been done a number of reconstruction schemes for inverse boundary value problems, for inverse scattering problems. And today he's going to speak to us about a reconstruction scheme for active thermography. So please.
Okay. Thank you for the introduction. This is the contents of my talk. First, I will explain about some important preliminary estimate which I need for the later argument. And that is especially how to get some gradient estimate of fundamental solution for parabolic equation with discontinuous coefficients. And then I will move to the so-called active thermography, and I will propose some scheme for doing that, which I call dynamical probe method. Okay, let me start with important preliminary estimate. This is a joint work with Jishan Fan, Kyon-san Kim, and Sei Nagayasu. Okay, the domain and operators which I use are the following. Omega is a bounded domain which can be considered as a heat conductor with a C2 boundary, partial omega. And the heat conductivity gamma is defined everywhere in omega, which is symmetric positive definite, satisfying this kind of estimate. We further assume the followings for omega and gamma. Omega consists of subdomains dm. So you can see this picture, omega consisting of some subdomain d1 to d4. For each separated subdomain dm, I assume dm is of C1 alpha smooth. And also, when we consider the conductivity restricted to this separated domain, I assume its smoothness is C mu. And for the non-separated one, I consider those smoothness in the limit of the separated one. Okay, here is the gradient estimate. Let omega prime be a compactly embedded sub-open set of omega, and T0 in a open time interval 0 large T. And then consider any solution U to this parabolic equation. Gamma is the previous conductivity. And then we have the following interior estimate, which is of this form. Okay, we have so C1 alpha prime regularity with respect to space variable. And this can be estimated in terms of the L2 norm of the solution U. And what is important here is this constant C is independent of the distance between the inclusions. So this estimate still holds even these inclusions are touching. By using some scaling argument, we can derive from that previous interior estimate the following point-wise gradient estimate for the fundamental solution of our parabolic operator with discontinuous coefficient. We have this kind of estimate which is exactly the same as the usual estimate for the fundamental solution for the heat. Okay. Okay, let me give you some remarks related to the result. So we can also obtain a similar estimate for non-homogeneous parabolic equation, which means there is some non-zero right-hand side of this form. Recently, Haigan Lee and Yang Lee extended the result to time-dependent parabolic system. But the assumption they put on the inclusions are independent of time. So the inclusion will not move respect to the time t. So they gave their own proof, but there can be another proof based on the estimate we already derived in the case that the coefficient gamma is not depending on time t. For that, you only have to consider this kind of ft, xt, ys, where f tau is defined via E tau. E tau is a fundamental solution for the operator with coefficient freeze at t equal tau. So the time-dependent inclusion, which means that this small, the sub-region dm are moving with respect to time t. In such a case, the gradient estimate is open. It's an open question. Let me tell you some history behind these gradient estimate. First, there was an observation made by Babuška and his collaborator in 1999. He considered elastic equation numerically, the equation having some discontinuous coefficient, and they observed that the gradient estimate of the solution does not blow up, even in the case those discontinuity are touching each other. So he made a conjecture which is called a Babuška conjecture. And then first for the scalar case, Lee and Vogelius proved the gradient estimate, which means that in the mechanical terminology that the stress is not blowing, even the inclusion are touching. And then after that, Lee and Nierenberg really proved for the elastic system. Okay, and then now comes the some result for the parabolic system, which was really proved by Lee, the two Lees, Haigan Lee and Yang Lee. Okay, so the idea of the proof consists of two ingredients. One is some interior estimates. Another is the applied Lee-Nierenberg estimate. Okay. What are the estimates? Let omega tilde compactly embedded open set in omega, and T0 is in open time interval 0t. Then any solution U to this equation in this cylindrical domain Q has the following estimates. We have three types of estimate. The first one is the standard estimate. The second one is a D. George type estimate. And the last one is the Radzinskaya-Rybkin-Uralcheva type estimate. Okay, we will use these three types of estimates. Okay, let me get into the proof. So first we define a series of subdomains omega tildes and also some series of deltas. Then by the previous estimate, we have this one. This is the standard estimate. This is the Rajdenska-Rybkin-Uralcheva estimate. And then further, we differentiate the equation and consider the equation for u sub t. And because gamma is not depending on t, the u sub t satisfy this kind of equation. And then we use this George type estimate, and then we further use this Rajdenska-Rybkin-Uralcheva estimate to get this kind of estimate. Okay. Then next we move the ut in the original equation to the right hand side, and then we will apply the Nierenberg estimate. Okay. And then you have this C1 alpha prime norm of this u at time t can be estimated like this. And then we take the soup with respect to t in the interval delta 2 to large t. Then this can be further estimated as follows. Okay. And then we use for the second term the previous the estimate 3 stars, and this we can use this estimate for the first term, and then we will end up with this estimate. This is the proof. Okay. Okay, let me move to the active thermography and dynamical probe method. Okay, so first of all, what is active thermography? So suppose you have some heat conductor omega, and there could be something inside. It could be inclusion. And then the active thermography will inject some heat flux from outside, and then measure using infrared light camera the distribution of the temperature on the surface of omega. And then with this measured data, the active thermography will detect what is inside this omega. So what's the principle of this active thermography? Let me explain you using this picture. Suppose you have a heat conductor of this rectangle shape. And also, let's suppose that there is some inclusion inside which is less conductive. And then we inject some heat flux using a heater or a flash lamp, and then measure the temperature distribution on the surface of this rectangular shaped heat conductor by infrared camera. Okay. Then because this inclusion is less conductive, the heat flux will be stacked above this inclusion. So that you can imagine there will be some temperature higher above this inclusion compared with the other part. So you will have this kind of a temperature profile. Okay. So so looking at this profile, maybe you could see where could be this inclusion. So this is the principle of active thermography. Okay. Next, I want to explain you the scheme I'm proposing for this active thermography, which I call dynamical probe method. Okay. I also considered for the case the conductivity is anisotropic. Okay, let me set up our argument. First, let omega be a bounded domain in Rn, and n can be any physical dimension, which means n is 1 from 3. And I assume its boundary is C2 for n equal 2 and 3, and the boundary consists of two parts. Here's some picture. So this is the omega, and when we consider the boundary of this omega, it consists of two parts. Gamma d, this is the red part, and the white part, gamma n. Okay? And there could be some inclusion inside. Okay. So for the inclusion D, I assume the inclusions are now separated inclusion. I'm not considering the non-separated inclusions. And then I assume for this D, first its boundary is of C1 alpha. And I also have to assume omega minus dy is connected, which means the boundary of D can be observed from outside. So you don't have any inner hole in this separated inclusions. And also, I have to assume D is not touching the boundary of omega. For the heat conductivity, denoted by gamma, I assume it has the following form: A plus A tilde minus A times characteristic function of D, which gamma, this gamma, first of all, must be positive definite for each x. And also, I have to assume that the conductivity must have some clear jump across the boundary of inclusion. So, A tilde minus A is always positive, definite, or negative in a neighborhood of partial D. And further, for the smoothness of A and A tilde, I assume they are C1 of omega bar. Okay, for the function spaces, I use the usual notation for the usual Sobolev spaces. They are HP, HPQ. But for instance, let me explain you for instance, HPQ omega times the time interval 0t. This is defined as follows. The element G belongs to this function space if this norm is finite, and this norm, the index Q denotes the regularity with respect to the t variable, and P describes the regularity with respect to the total derivative. And how you count the total derivative is according to this kind of a summation. So if you have this kind of a derivative, you have to count the order of this by multiplying the derivative, the order of derivative with respect to t by 2. I also use this kind of a function space. This is a function space for function which takes value in this HP partial omega function space. Okay, the fourth problem for the active thermography can be described as the following mixed problem, which is given f and g from these function spaces, asking whether we can have a unique weak solution u in this function space w of omega sub t, which is defined as follows. So the u must be first in h10 omega t, and also the t derivative of u is in this function space. Here h1 omega star is the adjoint space of h1 omega. And then the equation and the boundary condition and the initial condition are given as follows. Okay. Here, the nu here is the outer unit normal of partial omega. So this partial A just means this is the conormal derivative of this the elliptic operator. And also these function space, I use the Hellman's notation of Sobolev spaces. So for instance, this means it's in H minus 1, the usual H minus 1 half space, but its support is in gamma n bar. And this is just a distribution which can be always extended to the whole partial omega from gamma d, and which belongs to in the usual sense H1 half. I also use this kind of a notation omega t and partial omega t for the cylindrical sets. So for instance, omega t is omega times time interval 0t. Anyway, this mixed problem is a well-posed problem in this function space. Okay. So based on this well-posedness of our forward problem, we define the Neumann to Dirichlet map lambda d, which we will take as our measure data. This map is defined as follows. First, we fix the f. F is Dirichlet data on gamma d, and then define this map lambda d as a map which is sending this G. G is Neumann data to the Dirichlet data of the solution on the same boundary, gamma n t. So we are fixing the data on this gamma d, but we are varying the data on gamma n and making the measurement on gamma n. Okay. So taking this lambda d as our measure data, our inverse boundary value problem is as follows. Reconstruct the unknown inclusion d from lambda d. There are some known results. First, Beru showed the local uniqueness and stability for one measurement. And then next, Ilyanin Isakov started the whole business. They show the global uniqueness to our problem. And then D. Christo Becerra showed the optimal stability estimate for the isotropic case. And this is even for the time-dependent inclusion case. And then there are some results by me and my collaborator, especially doing the reconstruction schemes. And I also want to mention there's another type of work by Ikehata and Kawashita. They extracted some information of the unknown cavity. They consider not the unknown inclusion, but they consider unknown cavity by one measurement. Okay, so let me next start explain you what is dynamical probe method. Dynamical probe method need to use several kind of things. They are fundamental solution, also Runge's approximation, reflected solution, and indicator functions. So, so let me first define fundamental solution. So I denote by gamma and gamma star the fundamental solution of our operator without inclusion. So in the case there isn't any inclusion, I put empty set. So P empty set is the case there is no inclusion. So we don't have A tilde here. So A was just the background conductivity, okay? And this A is known. The same is as for this gamma star. And then we will cook up this gamma and gamma star a little bit to consider another G and G star, which satisfy some condition on gamma T D. Okay. I want to set this G and G star to have 0 on gamma sub T sub D. Okay. But this G and G star still have the same type of singularity at the singular point y and s. Okay. Next, I want to explain what is Runge approximation. This is an approximation which approximate, for instance, this G. G is quite similar to the fundamental solution to our background operator. So this sequence B sub ys 0j approximate this G in some approximate domain U times the time interval minus epsilon prime T plus epsilon prime. But this B satisfy this background equation in the whole domain. Okay, and there are some auxiliary condition, but it's not so important. But what's important is what is the approximate domain. So first, this epsilon prime is smaller than this epsilon. The previously given this epsilon, and also this open subset U of omega must satisfy some conditions. The conditions are given here. The important condition is again omega minus U bar must be connected. Okay? Because this Runge approximation is using the unique continuation property. Okay? Also, to handle the fixed data f and also the g, I also have to consider some v and psi, which are the solution to these mixed boundary value problem. And then I define another sequence. For instance, the bjys is the sum of b and the previous b0jys. Okay? And then, of course, this will converge to this capital B sub ys, which is defined by small b plus the g in this approximation domain. The convergence can be of H21 UT topology. I will call these sequence of functions bj and psi Runge's approximation functions. Okay. Now, let me define the so-called pre-indicator function. Let bj and psi be the Runge approximation functions I defined before, and then I define the pre-indicator function I of y prime s prime ys by this formula. So there are Runge approximation functions here, and here. And also, please note there is our measure data lambda d here. Okay. This lambda d means that lambda d of, say, partial a vj ys something means that to define this lambda d, we are using as a Neumann data this partial a vj ys. For this limit, we only consider the limit whenever it exists. Okay, and then the reflected solution can be defined as follows. First, consider the solution U with the Dirichlet data F and the Neumann data. Here we have this Runge approximation functions, and denote this U by uj sub ys, and then consider the difference of uj and vj, which I denote by this wjys, then we can show if y is not in d bar, then if we take the limit with respect to j, this wjys will converge in this function space to some w. And we can further show this w will satisfy this mixed boundary value problem, mixed problem. Okay. I will call this the limit w reflected solution. The importance of this reflected solution can be seen in the next theorem. We can represent the pre-indicator function using the reflected solution in the following way. Okay. Later, we will take y and y prime equal and let y tend to the boundary of D. Then, due to the fact that the singularity of the parabolic equation will not propagate, so this integral term is always bounded. So when we are looking at the behavior of this pre-indicator function, when we take y prime equal y and let them tend to partial omega, the behavior can be totally controlled by this wys y prime s prime. Okay. So now I want to define the indicator function and want to state our main result. First, I will introduce some C1 curve which is non-self-intersecting, parameterized by the parameter lambda. Lambda moves from 0 to 1, and this the curve C is in omega bar, and it has two endpoints C0, C1 on the boundary of omega. I will call this curve C a needle. Okay. And then for each C lambda, which is the point of this needle, I will define the indicator function j of C lambda s by this formula. It's, I'm taking the two limit, which is really impractical, but this is the way to define it. So let me show you by some picture. Here's the C lambda along this needle. So needle is this one. It's just a non-self-intersecting curve joining the 2 points of the boundary of omega. So C lambda is a point on this curve, and then I consider a point, a nearby point, C lambda minus delta. Delta is very small. And then for this C lambda delta, I am considering this pre-indicator function, and then take the limit with respect to delta and also epsilon. Okay. Now, this is the main theorem. Okay, so first fix S, and then consider the indicator function. If the needle will not intersect with the D bar, then this indicator function will stay always finite. But if the needle is touching, is intersecting with the D bar, then we will know that the indicator function will blow up at the first hitting point of the needle to the boundary of D. In a complicated way, you can describe it as follows, but essentially it is how I explain you. Okay, so so we can use this. Maybe let me see. Let me. Okay. So we can use this theorem to get this intersecting point. That is, so we move this C lambda starting from C0, and we observe how the indicator function is behaving. And then we will know at this first hitting point that the indicator function will blow up. And then this is the place we can locate this intersecting point. So if we take several needles, then in principle we should be able to get all the boundary point of D. This is this dynamical probe method scheme. Okay. So let's see. Let me tell you a little bit about the proof. I will explain you only for the case n equals 3. Okay. And then please remember what I said before. First of all, there was a representation of a pre-indicator function using the reflected solution. And I already explained the behavior of this pre-indicator function is the same as that of this reflected solution. And then how does this reflected solution behave? Reflected solution was satisfying this mixed problem. And then you can see on the right hand side of this equation, you have the V. V is defined via the fundamental solution. This is almost the same as the fundamental solution. And this Ys denotes the location of the singularity of the V. So this left-hand side is blowing up if Ys tend to this partial D. Okay? But combining what I explained you and also what I explained you, if y is away from this partial D, this will never blows up. Okay? Sorry, I have to say if this y taking y and y prime equals 0, okay, and if y is not is away from partial D, this will never blows up. So what we have to show is for the case y is close to partial D. Okay, for that, first please consider this kind of a situation. So we have a needle going into D, and let the first intersecting, first hitting point of this needle to this partial D is P. And this can be also denoted by C of lambda 0. And then we consider a nearby point of this P, which is just a point before this point P, which is X. X also it's also equal to Y, given as C lambda 0 minus delta. Delta is a very small positive number. Okay, and then in this neighborhood, I will make some a change of local coordinate, which can flatten this part of the boundary which can flatten this part of the boundary, and then I will denote. So this space I use the X, and in this space I use psi, and also for the Y. I used eta in this new space. Okay. And also, sorry, the inclusion part will be transformed to the lower half space. Okay. Then. I have to define several fundamental solutions associated to several operators. They are these operators. But what is important is the third and the fourth operator. Okay. So these are the constant coefficient operator. Okay. Okay, and then we decompose we express W. Well, first of all, W can be expressed as the. I have to go back. Okay, first this was important here. If we consider W plus V, it's easy to see this E is a fundamental solution for P sub D. Okay, and then having this in our mind, we rewrite this W. Of course, W is given as follows, but we rewrite this expression in the following way. Okay. Then we can see this the fourth term. With red color. This is the dominant part. For the behavior of this W. Okay. Well, I will skip all of this. Okay. Well, that's the. I'm not giving completely the good explanation for the proof, but that's the key. Okay. Okay. So let me give you some remark. So the previous proof. For the separated inclusion case works well, except for the final estimate W. W is the this guy. This the difference of gamma minus 0 minus gamma 0. This is the W. We cannot give the good estimate for W for the non-separated inclusion case. All of the rest, all of the rest of the argument can work even for the non-separated inclusion case. Okay, so what about for the isotropic conductivities? So in this part of my talk, I would like to show you that there's a possibility not only identifying the shape of D, but also you can identify the conductivity inside. If the conductivity is uniform inside. Okay, what I mean by the isotropic is the following. The conductivity gamma is a scalar, and I also assume this conductivity is of homogeneous. Okay, so the K is a constant, just a constant. And I assume K is positive and different from 1. Okay. Then the argument will be exactly the same as before. We only have to look for the dominant term of W for its behavior as Y tends to partial D. Okay. And we will again know the dominant part which controls this behavior is coming from this guy. Okay. Because the xi and positive is this part, which means it's outside of this D. So I only have to see the behavior of the xi and positive part of this W. So I denote that one as W plus. Okay. And so I want to see how this W plus behaves. Okay. So for this isotropic case, when I assume n equal 2 and 3, W plus has some explicit form. And also it can have the explicit form when we take the delta to 0. Okay. So for instance, for k larger than 1, this limit can be given as this form with Hn of this form. Okay? When k is in between 0 and 1, oh, I forgot, please, this is a mistake, please don't take the absolute. The limit can be given in this form, and this h and k has this form. Okay. So using this explicit form, we can have the following. For the case k larger than 1, we can prove this guy. Let me go back again. Here for k larger than 1, this is just a constant, and you have this guy. Okay, and this guy can be proved to be monotone increasing. Okay, monotone increasing. So for k larger than 1, using this property, we can also get the k from the measured data. However, for the case k is in between 0 and 1, we can only recover k from the measured data for those k in some certain interval. Nevertheless, for n equal 2, we can show this one, which appeared here. I'm sorry, I forgot to take the square root here. So square root of this times this is convex. Okay. Oh, sorry. Okay. Okay. So we can still use its property to do some kind of identification. So maybe I should end, or let me show you some picture of HK. So always, if k is larger than 1, hk is negative. Okay. So this is the graph of hk, and okay. So this is the first graph is the graph for the hk for k larger than 1, and also for the two-dimensional case. And this next graph is also the graph of hk for the case k is larger than 1, and for three-dimensional case. So it has some kind of similarity. And then this is the graph of hk for the case k is in between 0 and 1, and two-dimensional case. So then you have hk positive. But for three-dimensional case, it's hard to write the graph, because you have to, if you do by hand, you will end up with some kind of elliptic function. Okay, this is about the derivative for k larger than 1 two-dimensional case for this one. So you can see it's monotonically increasing. Okay. And this is for the case k is in between 0 and 1. Then the derivative will change its sign. Okay. But still, the graph itself is the graph of hk itself is convex. So we took the so the graph of this guy can be seen to be convex, as you can see from these pictures. So this part is just a zoom up of this flat part. So you can see it's still convex. Okay, for you have this picture is the graph of the derivative of this square root k minus 1 times hk for the case k is larger than 1 and three-dimensional case. So it's also monotonically increasing. But when we take the k in between 0 and 1, for the three-dimensional case, again the derivative will change the sign. Okay, this is some zoom up for the for this part. Okay, for the taking the second derivative for the 3D case, when k is in between 0 1, it becomes hard to show as a graph. So this is some zoom up, but from here we don't get any valuable conclusion. Okay, well, that's all. Thank you for your attention.
Okay. Questions? Comments? So, in this case, as I understood, you have several inclusions, but in each of them you have the same K. In the isotropic case, there will be several obstacles or only one?
Well, it's you can have many inclusions.
But in each of them would be the same.
Because it's this scheme is really pointwise.
Mm-hmm.
So if it's separated, you can treat the inclusion separately. So if the conductivity for each inclusion, they can be different, but must be uniform. Or if you just want to get the value on the boundary of the inclusion, then still it's okay.
And I missed this part. How did you relate these estimates you show us at the beginning in the proof?
You mean the preliminary estimate?
Yeah, how they come?
Let's see, how to relate them. Oh, okay, I see, I understand. Okay, here, so I rewrote this the expression of W in this form, and then how each term behaves is given as follows. But for the terms from the first term to the third term, we need to use the pointwise gradient estimate. This way I'm using.
And it has some relevance that because the estimates, the domains are C1 alpha, but you get that the gradient is controlling the C1 alpha prime.
Yeah.
Is this relevant that you use some, that the alpha are not the same, or is not important?
Well, that's okay, because I assume A and A tilde is C1. And the gradient estimate, you only need the C mu. Mu is
this number, which is 2 alpha or alpha plus 1.
So the result in the theorem itself is giving more stronger estimate, but what I need is just a gradient estimate, pointwise gradient estimate.
Okay, more questions or comments? Now do you just thank Prof. Nakamura for a beautiful talk.